All right, so hi everybody, I'm Jon. I'm the architect of Vespa, which I'll talk about today. So Vespa is a platform in the big data ecosystem, and I usually use this way to introduce it, to talk about its role in the larger ecosystem. When you start working with big data, you usually, before you start working with it, you just, if you have some system, you generate data somehow, but you don't really use it, which is this level, right? And then at some point you want to use your big data to do analysis, and the way you usually start then is you have you use your data to do visualizations and statistics and so on that informs humans that make the decisions about what to do about it. At some point you want to learn decisions automatically, and that's when you start using things like Hadoop and machine learning and so on to automatically learn what decisions to take based on your data. But it's still all happening offline. So a good example is if you do recommendation at this level. When you do learning, you do the learning offline, so you learn, for example, a list of movies or whatever that you want to recommend. But the learning happens offline, and the serving is just taking those static lists or recommendations that you learned and serving them, right? But at some point you want to start making decisions based on your big data in real time, as the user is making an action, for example, viewing a web page or doing something in an app or something. That allows you to build richer features. For example, in the case where you do personalized recommendation, you can move from recommending a list of something for some small segments or users to actually recommend personalized recommendations for each particular user based on their particular interests. That's not possible if you do everything offline, because you need to compute a list for every possible user, while if you do it real time, you only compute the stuff that you actually need based on what users are doing, right? So if you want to use big data to make decisions in real time, what you need, obviously, to make actions in real time, which translates to making decisions with really low latency. Because some end user is waiting, you usually have a latency budget of something like 100 milliseconds. You usually need to handle, while you're doing this, you need to handle continuous changes at a high rate to the data, because you want to be up to date with the changes that happens in the world. Because you usually have many users doing many things, you need to scale to a large number of requests per second. And because end users are directly exposed to this, you need a system to be always available. So you need to be able to make changes, recover from failures, add nodes, remove nodes, change schemas and so on without any downtime to the system. Lastly, this system needs to function in the larger big data ecosystem to integrate with things like Hadoop to do data feeds, Tensorflow and so on to serve models and things like that. So Vespa is a system that provides those features. So that's its role in the big data ecosystem. It was developed originally at Yahoo in the web search division, same as it started it just before we started Hadoop, but the IP rights around search are really, really nightmarish. So it took us almost 15 years to be allowed to open source it. We actually waited for some of the patents to expire. So now it's open source. You can find it at vespa.ai, and it makes those features on the last slide available to everyone. So what is Vespa in more detail? It's a platform where you can do low latency computations, often involving learned models over large evolving data sets. So you typically use it if you want to evaluate some machine learned model over many data points. The prototypical example is search over big data sets, things like web search, right? Because you have lots and lots of data and you can't pre-compute the answers to all the queries. You have to compute them as the user submits a query, right? Because there's just too many potential queries. And you want to use machine learning to do the ranking, right? So that was the first application that was economically very important, that had these problems. So that's why a lot of investment went into solving it for search. But now that we have it, we also use it for other things like, example, recommendation and personalization. So Vespa allows you to do search over unstructured textual data and selection over structured data, and then a combination of the two. It does relevance scoring, natural language, advanced ML models, Tensorflow, and so on. You can do query time organization and aggregation of all the data. And you can do all of this while you are sustaining a high write rate to the data. Typically, each node can do a couple of thousand writes per second. If you want to change your hardware, you just add and remove nodes to the clusters, and Vespa will automatically rebalance the data in the background while it's handling the writes and the queries. So no downtime required. There's also a Java-based processing logic container where you can add your own Java components if you like. And because these systems can be complicated and consist of hundreds of nodes and clusters and so on, well, not hundreds of clusters, but handful of clusters and hundreds of nodes. You don't want to set all of that up manually. So Vespa has a management subsystem that manages all the nodes and clusters for you. So in my company, which is called Oat now, it used to be Yahoo, but we merged with other companies and changed the name. We use Vespa for all the use cases that are somehow in this space. In total, we serve a couple of 100,000 queries per second over a couple of hundred, really, billions of content items. So one example application is the Yahoo front page, where the articles and media items that you see when you visit the front page is computed on the fly by Vespa based on your personalized profile. And also the ads that you see in there are computed by a different Vespa application based on your ad relevant profile as well as bidding information and so on. So some comparisons to other systems sort of in the same space. Vespa's focus is, as I mentioned, on big data serving, which means a focus on large scale, high availability, efficiency with many queries, bounded response times, and machine learned models. Elasticsearch is probably the closest alternative out there, but their focus is more on analytics, ingesting of logs and other kinds of time series data, things like that. Then we have Solr, which overlaps with natural language search capabilities of Vespa. And you have databases, which also slightly overlap, but obviously have no information retrieval and relevance and so on. And then we have things like Hadoop, which are complementary to Vespa, obviously, because they are not for serving, they are for the offline piece, right? So some more details about comparing with Elasticsearch. So both engines have text search, relevance, grouping, and aggregation, and so on. Elasticsearch have features more geared towards analytics, so that influence what is easy and efficient to do with Elasticsearch, while Vespa has features more geared towards big data serving. So typically make those use cases cheaper and easier to do. So some more details about the differences between analytics and big data serving. With analytics, you typically have a latency budget of a couple of seconds, because the user of your analytics system is typically somebody inside your company that is paid for waiting. While if you do big data serving, the user is somebody outside that don't have the same patience. And with analytics, you usually have a low query rate, while with big data serving, you have a high query rate. Analytics typically time series data, while Vespa is usually used for data where you can do random writes to the data later. More focus on high availability. And the flip side of this, because all of these are where Vespa is better, right? But the flip side is you can index petabytes of data with search, while that amount of data typically becomes very expensive with Vespa. Vespa scales, so it can do it, but it will be more expensive than Elasticsearch because it prioritizes these features, right? So that's the high level difference. And lastly, with analytics, you want to put a focus on visualization of the data and so on. So Elasticsearch has stuff for that, while with Vespa we don't. We're focusing more on integrating with machine learning and so on. So onwards to the architecture of Vespa. Vespa is a two-tier system. So you have, on the top, you have a stateless Java container that handles all the incoming document operations, get, put, and so on, and also handles the incoming queries. And inside the stateless Java container, you can add your own Java components, but there are also components that lives there by default. Then we have content clusters that actually stores the data and executes the distributed part of the queries. Because this is hard to set up manually, we also have an administration cluster that sets up and manages these clusters and nodes and processes and so on for you. So what the users see is what we call an application package on the left there, which is a more abstracted view of the application that you want to run. So you write your application package, put your Java components if you have any in there, your schemas, your machine learn models and so on, and then you deploy it to Vespa, and Vespa will realize that system using the available nodes that you give it. If you make a change to your application package, you just deploy again, and Vespa will carry out the change without any downtime. So I mentioned that the most important feature of Vespa is to be able to bound the latency of computation, regardless of the size of your data and the complexity of your machine learning models and so on. So how does it do that? Obviously it's mathematics, but there's three main things. One is parallelization. So with Vespa you have multiple content nodes that stores different shards of the data. And obviously you execute the query over all the shards in parallel. On each of the nodes, we execute each query or multiple cores at the same time for different parts of the data space on that node. And the second thing we do is the critical design decision that is the same one that we made for Hadoop, which is rather than sending the data somewhere for computation, we send the computation to the data, right? So if you have, so the query represents the computation that you want to do, and in contrast from a traditional two-tier system where you just look up the data in a database and process do your processing in the stateless application container tier, you send the query down to the nodes, to all the content nodes that will execute their part of the distributed computation. And similarly with machine learned models, we take your machine learned models that are part of the application package and distribute them, send them to all the content nodes when you deploy your application. And then we execute the models with the local data on the node before we send it back up. And that allows us to scale execution independently of your network bandwidth, right? Because otherwise, if you want to evaluate a model over, say, 1 million data points, you need to look up the 1 million data points, send them to the node that will execute your machine learned model, and that just doesn't work because you run out of network bandwidth. I mean, it doesn't work if you want to have low latency. Okay, so this was a short introduction. I'll switch to another presentation that goes into more detail because we have a half an hour more. Just mention that Vespa is available on vespa.ai. There's a quick start there you can run that allows you to set up and run the whole thing on a Mac or AVS or even on Windows now in less than 10 minutes. So trying it out is pretty simple. Yeah, here we are. Okay, so this deck goes more into details about how you actually use Vespa. So if you want to run Vespa, you can either take our RPM packages that we distribute and install them, or you can use the Docker image that we also provide. All nodes have exactly the same image or packages, and it's Vespa that knows the role of each of the nodes and starts the write processes and so on based on the role of the node, right? So the only thing you do locally on the node is get the Docker image or install the RPMs and set a single environment variable that points to the configuration servers of Vespa that will tell the node what it should do. And everything else that turns a set of nodes with Vespa installed into an actual running application is contained in the application package. So using Vespa is creating the application package for your application. So it contains the configuration that tells it what clusters to run, the schemas, the machine learned models, everything. And also Java components. And as I mentioned, once you change it, you deploy again, and Vespa will affect the changes automatically, including Java code changes that will happen without any restarts and so on by hot swapping the code. So what goes into a minimal application package? You need 3 files, which are shown in simple examples in completeness on these 2 slides. So the most important one is what we call services XML that defines the clusters that you want to run and what they should do. So in this simple example, I have a single stateless container cluster where we can say what components we want to load and run in this container. In this case, we run the search middleware that provides the search API and so on. And we run the document API that allows you to get and put and so on documents. And then we just list the nodes that should run this container. We also here have a single content cluster where we have to say how many copies we want to store of each piece of data for redundancy. And we list the document types that we want to use and a set of nodes again. And then we have the hosts XML file that just lists the hosts and gives each of them an alias that you can use in services XML. Lastly, you need your at least one data schema. In this case, it's called music. A schema is just a collection of fields. And for each of the fields, you say, do you want to index that field? Do you want to show it in the result? Things like that. And it also contains your what we call rank profiles that define what you want to compute over these documents when you're matching and ranking them. And this can be a simple handwritten mathematical expression, as in this case, or it can refer to a Tensorflow model or something else. So that's all you need to create an application. When you're calling Vespa, you can put documents by posting them to a URL starting with document v1 and continuing with the document ID. And the document is just a collection of fields. So this is the JSON for a simple document. There's also a standalone Java client that you can use either from Java or from the command line to feed much faster than you're able to do with posting like this, because it multiplexes over multiple HTTP channels for you. And you can obviously get documents using the same URL, but get. And this is a very simple example of a search query. Operations. Operations in Vespa is still challenging because it's a stateful system, but it's simpler than many other stateful systems because we automatically redistribute data in the background. There's no single point of failures, so if you have enough redundancy, you can just lose nodes and you don't really need to do anything. When you lose a node in a stateful cluster, Vespa will automatically rebuild missing copies of data from the existing redundant copies and redistribute the data. So you don't really need to do anything, and you're not losing queries or writes just by losing nodes. You just need to make sure that over time you have sufficient capacity. We collect logs to the configuration server cluster from all the nodes, so you can look at logs there. And we provide metrics from all the nodes, so you can do your own metrics integration. Somebody recently contributed Prometheus integration, by the way, so that you can get out of the box now. Okay, so onwards to how we do matching. So there's three main things that Vespa do for you. One is matching, selecting the data that you want to compute something over. Ranking, which is the actual computation of some personalized model or recommendation model or relevance model or whatever. And then it's the grouping and aggregation part, where you can organize the data somehow and aggregate values over the groups that you organize and so on. So I'll go through each of these topics in order. So first, matching. The job of matching is to find all the documents matching a query, obviously. The query here is a term, it's a tree of operators. And the operators can be really simple, like the most obvious one is term, which matches a document if that token is present in the document. And then you have operators for combining simple term operators like and, or, and so on, as you would expect, and a bunch of more complex one I won't go through. And then we have some other category of operators that where whether or not you're matching a document depends on what other things you are matching. For example, range matches the n documents that have the highest or lowest value of some numerical field, or the documents in some range. And WAND is an algorithm that gives you the highest scoring documents based on a dot product computation between a vector in the query and a vector in the document without actually computing all the dot products for all the documents. It's a pretty clever algorithm that allows you to skip through the space of vectors without actually computing all the dot products. So there's two views of what matching is doing. One is it's selecting the subset of documents that you want to compute something over, which is the typical search use case, right? Where you're searching for something, so you only want to look at the documents that matches your search criteria. The other view is the more common one in things like recommendation, where you have some machine learning model that ideally you want to evaluate over every single document item, but that's too expensive, so you create some query criteria that filters out documents that the user are probably not interested in. And in that case, matching is more just to skip documents that are unlikely to be of interest. As I mentioned, the queries are evaluated in parallel over all the clusters, document types, data partitions, and the numbers of cores you configure for each query. We can accept queries that are passed from the outside, and there's an SQL-like language for doing that, or you can add Java components to build the queries inside Vespa from other information that you pass from the outside. So some more details about how queries are executed. The queries comes into the stateless container that will run a bunch of components that we provide that processes the incoming query and prepares it for execution. And here you can also add your own components to build the query if you like. Then it's sent on in parallel to all the content partitions where we do matching and the first phase ranking in parallel. There's also a second phase ranking, which is useful in the case where you want to allocate more of the CPU time to compute a more complex model for the most promising candidate documents, rather than allocating the same amount of CPU to compute over all the documents. After these phases, we do the grouping and aggregation over all the matches, not just the surviving ones. And lastly, the container will, across all the partitions returning partial results, will decide the final data to return to as response to the request. And at that point, you usually need to fetch additional data for each of those documents. So there's a final phase that does that. So what kind of data structures do we use on the content nodes to make this fast? We do what's called, in the search world, is called document at a time evaluation, where you step through the document space by looking at all the features of a single document at the same time. And the reason you want to do that is to have all that information available at one time, so you can compute non-linear ranking functions over all the features of a single document at the same time. For fields where you specify that you should build an index over that field, we create positional indices that consist of a dictionary plus posting list. The dictionaries are just a list of all the separate tokens, words, across all your documents. Those points to what's called posting lists, that are lists of all the locations of those tokens, words, in all the documents. And so this data structure is a reverse data structure, right, that allows you to look up the documents that matches a particular token without looking at all the documents, because you have a reverse list that lists all the documents for each of the terms, right? So that's the basic search engine trick to make things fast, right? The other thing we use this for is to compute a relevance score, because we have all the positions of all the tokens as well. So we use that positional information to compute a rank score that takes between the words into account and so on. So that's pretty standard search engine stuff, apart from the positional information in the indices, which most search engines don't do, at least by default, because it used to be expensive, but now we actually have the capacity to do it, and it makes it possible to have much better relevance in natural language ranking cases. Posting lists needs to be sorted, so you can look up in them really fast, but that means that changes to them becomes really expensive. But in Vespa you can do real-time updates. That means when you make a change to a document or add a document, the next query will reflect the change that you made. And those two things don't really fit together. So to solve both requirements, we also use standard database like B-trees in memory that contains all the recent changes to documents. And when we execute queries, we look at both data structures. And then in the background, we merge the B-tree to posting lists, and then we merge the posting lists, and that's how we are able to sustain this over a long time. So that was for index fields. We also have what we call attribute fields that are in-memory data only, that are stored in forward order. And that's useful because you can look up the values in those documents quickly during ranking and grouping and aggregation and so on. So it's typically used for structured data like numerical fields and categories, tags, and things like that, that you have room for in memory, and that is useful to access directly during ranking and grouping. Optionally, you can also do inverted indices in the form of B-trees over the attribute data if you want to use it as a strong criteria when you are searching. In addition to all this, we need a transaction log for persistence, because if you do some writes, they end up in B-trees in memory, right? And then if you crash the next second, we want to guarantee that the writes you made are persistent, right? So we store them in an append-only transaction log that we can replay when a node comes back up. It's a standard technique from databases as well. In addition to all of this, there's a separate data structure storing the raw data of all the documents that we use for redistributing data when you add or remove nodes, or we lose some node or disk or something. And they're also used for serving from the raw data as part of returning results to the users. If you have multiple document types, we have one instance of all of this for each of the document types in your content cluster. So onwards to ranking, the other big topic. A ranking expression is really a mathematical expression that computes some value for each of the documents based on what we call features. There's 4 kinds of features. There's constant features that you provide in your application package. There's features from the document, those attribute fields I just mentioned. There's query features that you send with your queries, and there's match features that are computed from the other kinds of features, or really from the data of the documents and the queries by Vespa while you're doing the matching. So what are the built-in match features? There's a bunch of features for doing text matching that takes the position of words and so on into account. Lots of features around that. Then there's features for geodistance, time decay, lots of other things. There's a long list on the documentation page. What if you want to do machine learned models? Some examples here. If you do search, you usually do machine learned models where you have training data that consists of pairs of documents and queries that have evaluations. So it's a kind of supervised learning. At least in Yahoo, we have been using GBDT models, gradient boosted decision trees, for this a lot. It turns out to be pretty good for ranking. And if those models can be represented as nested if functions. So there's, I didn't mention that, but one of the functions in our mathematical expression language is an if function, and that allows you to represent decision trees by nesting if functions. So those functions are nested ifs and sum of lots of these. And Vespa recognizes this function form and has separate optimizations for that. In recommendation, what people often do is they embed both the documents and the user in some vector space or tensor space, and your model computation is to combine the document and the query using either a neural network or a simple dot product or something. Yeah, I mentioned this already. So if you want to do that latter kind of advanced ranking models, you want to meet the Tensor math in Vespa. Back in the old days, we used to have all the features used to be scalar values, but that doesn't scale well to things like neural nets and FTRL models where you have millions of features and so on, because it gets pretty tedious to write mathematical expressions over these large sets of features if you only can use scalars. And it's also very hard to optimize. So we provided a tensor language or tensor model in Vespa for doing that. So what is a tensor? A tensor is really just an n-dimensional table of numbers for our purposes. If there's any physicists or mathematical people here, they will be offended, but that's the way we usually appropriate words from those areas in computer science. So a zero-dimensional tensor is just a scalar value. It's literally possible to write it like this in Vespa, but it's equivalent to just writing the number itself, right? A one-dimensional tensor is just a vector. Here you have a dimension called x, and you have some values for it. A two-dimensional tensor is a matrix, and then you can go to higher dimensions if you like, right? So in Vespa you have two kinds of tensor dimensions. You have index tensor dimensions, where the values are continuous from, really the labels here are continuous from 0 and are numeric. And then you also have what we call map tensor dimensions, where the labels of the dimensions are any identifiers, and that allows you to represent sparse models, right, where you have a really large space of possible values in some dimension, but you don't want to keep in memory lots of zero values, which you would do if you represented it as an index dimension. Then you can use map dimensions instead. So that's cheaper memory-wise and memory bandwidth-wise, but it's more expensive to compute with that kind of tensor dimensions, so it's a trade-off there. So the tensors might be in your documents. So this is a literal example from the schema that we looked at earlier, where you have a tensor field and you just supply the type, and then you can say the usual things about whether you want it to be an attribute or whatnot. You can send tensors with the query, is one example of that. Or you can add tensors as constants to application packages, which is relevant for tensors that are really part of your machine learned models, right? And usually those tensors are really big, so you can compress them like this. So what operations, what math can you do on tensors? Vespa provides 6 operations, and that is enough to do things like neural nets and everything that Tensorflow wants to do, except the learning part, which is not done in Vespa, and lots of other things. Map takes a scalar lambda function and applies it to all the values of your tensor. Reduce removes one or more dimensions of your tensor, collapses the tensor using an aggregator function like max, sum, average, and so on. Join takes 2 tensors and combine them somehow, where the values of each of the cells of the tensor are combined using this lambda. And this is kind of a superset of things like tensor product, cross product, all of those things. Because what you do here depends on the dimension names of these 2 tensors. If they are in the same dimensional space, so both tensors have the same names of their dimensions, then you just match all the cells in the 2 tensors, and you end up with a tensor with the same dimensional space as you started with. But if you have a different dimensional space in this tensor and this tensor, say this is xy and this is ab, then you end up with a 4-dimensional tensor ab x y, where you span all the combinations of all the cells from the 2 tensors, and the values are again combined using this lambda. But then you can also have all the cases in between, some overlapping dimensions and some different dimensions, which is quite neat. Because in usual tensor math, all of these variants become different mathematical operators because they don't have names for the dimensions, only implicit in. While in Vespa we have explicit names because computer scientists likes naming things, and that allows us to use the same mathematical operation for all these variants, right? You can also create tensors on the fly like this, which is tensor and a tensor type spec, and just an expression that generates a value for each of the cells. And you can rename some dimension to some other dimension, which is useful to influence what the join operation will do. And you can put some index tensors on top of each other, so to speak, concatenating them, for example, taking 2 vectors and combining them to a matrix, things like that. So some more slides on the tensor join operation, just because it's so awesome. Like the regular tensor product in math, it's associative, but because we name the dimensions, it's also commutative, which doesn't hold for regular tensor math. And that's really important for us because it allows us to do optimizations where we pick the order we do things in really carefully to make things efficient, right? Yeah, this is just an illustration of what I just talked about. Tensor product in math is for the case where you have non-overlapping dimensions. And then in math, you have what's called Hadamard product for the case where you have where you have completely overlapping dimensions, and those are the only 2 cases that are usually handled in math. But with the Vespa join method, you can do all kinds of overlapping cases where you have some dimensions that are the same and some that are different, which is really neat. So using these 6 operators, you can do you can combine them as building blocks to do all kinds of operators that you encounter when you do things like neural nets. So there's a long list on this documentation page, and for each of the higher order operators, you have, just for fun, listed the equivalent in Vespa. But you can use those higher level functions directly in Vespa. So Vespa will do the translation internally. So some use cases. This used to be very popular, at least just before neural nets took over. So this is, at least up until a short while ago, how Google used to do their ad ranking. So they used a model called follow the regularized leader, which is quite simple model. You have lots of features of the user, like the interest of the user, the location of the user, and so on. And you have lots of features of the document, like, for example, the topic of the documents. And then to do your learning, you generate features that are the combination of all these primitive features. So you have one feature which is a particular user location plus a particular user interest plus a particular location or whatever. And then the value of that feature is the multiplication of all those basic features. And then you do a logistic regression over these millions of features, and that's your model. So how do you express this in the Tensor language in Vespa? Well, to do the combination of the various feature spaces, you just multiply them together. This is just the shorthand in Vespa for doing a join, where the lambda is multiplication. So since these have different, all of these tensors here represent features, so they are one-dimensional and have different dimensional spaces. So when you multiply them together, you end up with, in this case, a three-dimensional tensor that combines all these, these three dimensions. And then to apply the learned weights from your logistic regression, you just multiply with a different tensor that have exactly the same dimension, and that will multiply all the weights of that tensor with the weights that you generated, and then you sum over that, and that's your complete model. So it's a really, really terse way to express this in Vespa. So this is literally what you write as your ranking expression in that case. Here's an example that I won't go through, which is a single layer neural net in Vespa, which is also literally exactly what you write. It's using the higher level functions that I showed earlier. Lots of people now want to do deep neural nets on Vespa, and writing this manually, it becomes pretty cumbersome. So what we have done now is to integrate with Tensorflow out of the box. We're also working on ONNX integration, which allows us to do to deploy models from PyTorch and so on directly out of the box. So what you do then is you just save your TensorFlow model in TensorFlow directly to the application package in a specified directory. And then you can directly reference it in your ranking expression. So your ranking expression can just be TensorFlow and the directory of your TensorFlow model, and then it will execute the model. So that can be your entire model, or you can combine it with other features and whatnot. For example, it's interesting to combine it if, for example, you're doing search, but you also want to personalize the results, then you can do a combination, right? So compared to TensorFlow serving, Vespa is slightly faster. We just released a blog post about this. It's slightly faster, but not all that much faster. But it's way more scalable because we distribute the TensorFlow model to all the shards that have parts of the data. And then when you execute the query, you evaluate on all the data nodes in parallel without sending the data anywhere over the wire, right? So you scale independently of your network capacity, which is nice. So if you only want to evaluate your model over a single data point, there's no point in using Vespa. You use TensorFlow serving, right? But if you want to evaluate your model over many data points, as for example in recommendation cases where you want to evaluate the model over all the items that you may want to recommend, right? Then it makes sense to use Vespa for it because it scales much better. Grouping aggregation, that's just one slide. So we're nearing the end, guys. That's just a Lisp-like language that you can add to your query that use all the results as a list, and then you can take that entire list and group by some attribute. For each of the groups you can compute some aggregate value, maybe do subgrouping and so on, right? So it's a language for doing that kind of thing. It's evaluated over all the matches, distributed over all the partitions, so we don't send the data somewhere and then evaluate, because that would be too expensive. So when you evaluate this, we don't actually evaluate it in the way it's written, because that would be expensive. That would be creating this list of all the matches somewhere, and we never have that list. So we evaluate it inside out, so to speak, so that we never have to send all the data anywhere. And this also incorporates things like sketches to do counting of unique values over all the partitions without any sending the data anywhere and things like that. Also some words on the logic container. Also just one slide. So as I mentioned, the upper tier of the two-tier Vespa system is a Java container. The lower content tier is written in C++ because we manage all the data there, and we don't want to run into limitations with garbage collection and so on. But the upper tier is Java, and there you can add your own components for processing incoming queries, processing the results coming back, doing multiple queries in parallel or serially or whatnot. And you can also process the incoming documents by what we call document processors, and you can add your own generic handlers if you want to expose a different API than what Vespa provides natively, things like that. It provides dependency injection for you and hot swapping of the code without disrupting queries. So if you make a change to a component, it uses the dependency injection to recreate the part of the dependency graph that depends on that component. And then once it's done constructing the new component graph, it will atomically switch new queries to use that, while it's still serving queries that are using the old versions of the components using the old code. And it embeds Jetty for HTTP because we don't want to implement our own HTTP server. Okay, so you can try it out at vespa.ai in 10 minutes on your laptop, guys. That's all the slides I had. Any questions? Everything's crystal clear, okay?
Hello, thank you for this great talk. I was wondering about making adaptations to specific languages. So you were referring to this, to an index lookup. Normally you would somehow stem normalized tokens, and that would be a language-dependent operation. So what type of flexibility would be there to do this?
Yeah, so if you want to use Vespa for natural language stuff, you want to do stemming, things like that, and that's obviously language dependent. So Vespa only provides stemming and normalization and so on for English out of the box. So if you want other languages, you need to plug in some code in Java that adapts to whatever you want to do. So there's a simple API, you can add it to your application package, and that's how it works.
Thanks.
I'm just wondering regarding the training. So how how does the model training look like? And do you do it in real time or it's like in batch mode?
So you don't do your training on Vespa. So usually you do training offline. So we don't do the training part on Vespa. You just deploy your trained models to Vespa. And usually you also have a feedback loop that uses signals from whatever happens on your Vespa system as input to your next training iteration, right? But Vespa don't provide all of that for you. Usually people use things like Hadoop to ingest those signals and do your training, and then you deploy to Vespa once you have a new version of your trained model.
Got it. Thank you.
Any other questions?
Was Vespa also used for running large web crawl indexes? And if so, for how many documents?
So we used to do web search back in the days, and then we also did the crawler, but we don't have the crawler anymore. We ditched it, but yeah, so we used to do web search. What was the question again?
For what amounts of documents, how many billions, and how many machines were necessary to enable this?
For the web search, that's a long time ago, so I don't really remember. The biggest index we have now is the image index that's used for Flickr and image search in Yahoo and so on. That's about 40 billion documents. And it's about 300 nodes as far as I can remember. Yeah.
So, and how much index data does one node keep?
Yeah, that's how much data on a node. So I'll give you the range. So in the ad application I mentioned, because their models are so crazily expensive, because it makes a lot of sense to spend a lot of money on finding the right ads. They only actually store about 300,000 documents, I think, on each of the nodes. While in the other extreme, which is the search suggest application we have for all of the mail users in Yahoo, where we use Vespa to do type ahead suggestions based on the personal data in your mail account. In that case, we have a couple of billion documents per node. So that's the range.
Okay, thank you.
Yeah.